Good morning. My name is Vishnuvardhan. I am from Electrical and Electronics Engineering. My roll number is 21951, capital H0246. My max TikTok topic is power distribution network optimization for one die regulator with Laplace transform techniques. Let's get into our topic. Abstract. This paper introduces a methodology to co-design on-chip linear dropout regulator LDO with power distribution network of package and PCB board based on Laplace transform method. A particle methodology demonstrates the effectiveness and efficiency of the Laplace model in the time domain and is derived that takes into account LDO PDN system impedance response. LDO pass transistor size and output decoupling capacitor optimization flow is progressed to meet the system voltage noise requirements. The goal is to provide sufficient performance for efficient system solution in the early stages of design and achieve success at the system level. Introduction. Time to market is very important for SOC's integration on package substrate, power delivery network (PDN), noise and supply noise requirements are important factors to the performance of chips and systems on chips. Due to small supply, noise value requirements and limited chips resources, power distribution network design remains a major challenge. Therefore, power distribution of chips such as decoupling capacitors and pure passive networks are not sufficient to achieve reliable power delivery on chip linear dropout regulator circuit is one solution for the shortcoming of pure massive power supply networks. In this paper, a methodology for chip level power integration analysis is presented. The approach accurately estimates the supply loss induced on a load current profile compared to the transistor level LDO block through the core simulation power distribution network and linear voltage regulator. We get the supply noise distribution map for LDO and PDN systems. This flow allows different design cycles to reduce fewer and quicker simulations and as a result because these are many iterations of the power integrity analysis to find the best solution. We analyze LDO pass transistor size and output decompiling capacitance area is optimized and we minimize the voltage noise with Laplace transform only. This paper is organized as follows. Section 2 describes the architecture and the low dropouts regulator circuit design with PDN of package and PCB board. Section 3 explains the proposed PDN impedance response modeling method in the time domain with Laplace transform techniques to solve related design issues. Section 4 represents the comparison between conventional simulations and the proposed methodology. The result shows great consistency between transistor level circuit result and Laplace transform. Accordingly, this methodology can be effective system level PI simulation solution that can analyze the super noise conductor performance of size and different pass transistor and output capacitor to precisely estimate the supply voltage ripple budget tendency in early stage of design development. LDO design introduction. Considering the scale down power supply voltage and higher data rate speed, one of the most challenging tasks for the system requirements is to maintain the integrity of in the deep submarine technology. One die LDO has to compact on its own challenging, including ultra fast load transistor power or current efficiency and high efficiency power supply radial rejection. Especially in this high-speed application, response time is usually required for the LDO output a good quality Supply voltage. The off-die path includes the parasitic package and PCB board path seen by the load as shown in figure 1. The operational transconductance amplifier OTA is shown as figure 2. This is about figure 1 on chip regulator PDN block. We can see band gap, package plus PDN board, supply node, etc. This is current mirror OTA type. Output impedance of LDO is a function of the off-chip and on-chip network as shown in equation 1. Error amplifier loop gain reduces the impedance characteristics of the feedback loop. The bandwidth of the LDO is in the range of hundreds of kilohertz. Therefore, the error amplifier can only adjust the output voltage up to hundreds kilohertz. Beyond the megahertz range of 1 megahertz, we can also rely on pass transistors and output capacitor for noise compensation. The PDN response is shown as figure 3. It uses AC simulations with IAC equal to 1 at load current element with the spice netlist and get the voltage response in the frequency domain, and it gets the PDN impedance result of LDO package and the PCB board. Z closed loop equal to Z open loop by 1 plus A loop gain. Figure 3 tells us about PDN impedance, the def response of one die regulator transistor level specific netlist package and PCBs parameter. Red line shows closed path PDN of LDO and package PCB. Blue line shows open loop PDN of LDO and package. Laplace transform function. The Laplace transform method provides an alternative method of correlating circuit behavior in the time and frequency domain and speed up simultaneous work in this domain. Laplace transit modeling is called by using Laplace in the source element. The Laplace transfer function is particularly useful in top-down system design. It uses a behavior transfer function instead of detailed circuit design. The Laplace transfer function can also be conventionally used in system level that contains nonlinear characteristics. Using Laplace transform can reduce the long simulation runtime of large complex designs such as LDO and PDN. The frequency response can be expressed in the form of a frequency table. The proposed method uses Laplace transformed frequency response data, which is used in general SPICE tools to convert the frequency domain response to the time domain response as a linear function block for a simulation SPICE. The y of t as supply voltage ripple is a conventional of x of t as load current waveform with the impulse response ht. So yt equal integral of minus infinity to infinity x of t into h into t minus t into dt, where the h of t can be received from h of f as system PDN impedance response in the frequency domain of one die LDO and package and PCB board as figure 3 by the inverse Fourier integral as shown below. Ht equal to integral of minus infinity to infinity capital H of f into e power j into 2 pi ft df. This case uses Laplace transform function to represent the impedance response of PDN in the model. Then connect load current profile source to the input of the model and to see its input and output. Verifications of the proposed methodology. In this chapter, we validate the proposed power integration analysis methodology through comparison with the transistor level SPICE result. For a precise comparison of the PI simulation Accurate models of active components, passive components, board, package, and all need to be taken into account. Conventionally, we had used SPICE simulator with transistor level circuit for the supply noise evaluation in the past to check voltage noise budget. However, this method generally took extreme amount of simulation runtime with some cases taking up to even several days. In order to overcome this runtime issue, the proposed methodology uses an improved solution with Laplace transform model of PDN impedance in the time domain. Case 1 uses passive components, board, package, load current profile as figure 4 and LDO spice netlist to simulate on-chip supply noise. It shows the comparison between transistor level result and Laplace transform model result at output node of LDO. The transistor level results as figure 5 are 13.9 MV. Using the proposed method, the Laplace transform model results are 14.9 MV. A small difference of approximately is 6.7% as described in table 1. This is the figure 4 load current waveform profile of attacked noise current blocks. Y-axis and x-axis is time. Figure 5 LDO PD and AC noise result with proposed method 14.9 MV. Y-axis contains V, x-axis contains time. LDO transistors level AC noise result with SPICE netlist method 13.9 MV. Upper y-axis contains V and x-axis contain time. Blue line indicate AC noise result with transistor level netlist. Red line tells us about AC noise results with proposed method. Conventional and proposed method comparison. Using the proposed methodology as figure 6, we have gained an appropriate level of correlation and Effectian method. The power integrity simulation methodology consists of below steps. These steps include gathering system PDN impedance response, load current profile, which are listed as mentioned earlier. The results are combined analytically in the time domain to obtain the supply noise impact directly without mathematical conversion. The Laplace method can be seamlessly integrated into the original PDN flow and get results inaccurately. Load transition current profile to PDN analysis. Laplace model for LDO PDN system response. Figure 6 PDN analysis map conventional method lower, proposed method upper. With the Laplace model proposed for co-design of LDO and package of and PCB board, figure 7 illustrate the trade-off of the LDO pass transistor size and decoupling capacitors area for voltage noise budget minimization. Here, volt noise budget affects device reliability, jitter, and functional failure. The appropriate selection of design factors achieves the goal effectively in the short time with the proposed method. Figure 7 peak to peak voltage ripple counter map as a function of 1 by LDO output decap size and pass transistor size. In this paper, an effective PI simulation methodology that takes speed and impedance characteristics of LDO package and PCB into account for co-design is proposed. This produces speed ups the design flow to perform fewer and quicker simulation and because there are multiple interactions of the power integrity analysis to find the best solution in a short time. So this is the all about my topic. Thank you.